from IEEE ComSoc in 2021, the Wireless Communications Technical Committee Outstanding Young Researcher Award. These research interests are on cutting-edge problems in communications, localization, machine learning, and stochastic geometry. Thank you, Harpreet. I will leave you the floor.
Thank you so much, Anna, for this very kind introduction. And thanks also to Francois for this very kind invitation. I really wish I could make in person, but I think that will have to wait. So this presentation is going to focus on Poisson Line Cox process. We will define what that is. We are going to focus on its distributional properties and applications to vehicular networks. I was because it was too early for me here. So I'm not sure if this term has already come up in one of the talks before. So if it has, we'll just have a very quick refresher when we go through this. This work is joint with my highly talented PhD student, Vishnuvardhan Chetlur, who recently graduated and is now working on CV2X at Qualcomm San Diego. So thanks, Vishnu, for everything. And I would actually go on to say that I'm sort of filling in for him when I present this work. Okay, so in terms of this talk, the overview, I have 5 main messages that I would like to share with you in this talk. First is related to the historical perspective. So if we trace the history of this point process, we will see that there are some very interesting connections with the other areas, including statistical physics, some early on, and also some of the work from 90s from some folks who are on the call right now. So I will share that historical perspective with you first. Then we are going to look at the application of this model to vehicular networks. First, we are going to look at some Euclidean distance properties. For example, how do we study coverage of this model under the power law path loss model, where power law is in terms of the Euclidean distance, right? So that will be our second main topic. The third main topic is going to be load analysis, which will introduce another interesting stochastic geometry construction, which will be the interaction of this point process with an independent Poisson Voronoi tessellation. So we'll see how to do some type of, so how to study this interaction, and we'll also make some connections with the past work there. Then we are going to compare this model with 3GPP models. So how do we stack up this stochastic model and the 3GPP models which are used in 3GPP simulators? Now, time permitting, at the end, we will also study the path distances or path distance distributions of this process, and we'll see what those are and their possible applications to wireless networks. So everything that I'm going to present and a lot more is available in this short research monograph that Vishnu and I wrote. It was published by Morgan Claypool in 2020. So if you're interested in this topic, or if I manage to pique your interest during the talk, this would remain the key reference for this work. Okay, so let's first motivate this model. In many applications, wireless nodes are constrained to lie on line segments or lines. Think of a vehicular network, for example, right? So your vehicles are constrained to lie on roadways. Now, this construction is not limited to vehicular networks. It also appears in robotic systems, for example. Say you are deploying some robots to inspect underground pipe systems. Right, so pipes are linear. That's right. So they will. You can think of a pipe network as a collection of line segments, and again, the movement of robots is constrained on those line segments, right? And it turns out that these lines could themselves be irregularly placed on the plane, right? So these lines are not going to form sort of a nice grid pattern. Think of a road layout. I have this picture, which is from our university campus here in Virginia Tech, and we noticed that there is some collinearity, but the line segments are somewhat irregularly placed. And one of the models, again, one of potentially many models one can use to capture this irregularity is the so-called line process. And this line process has been of interest to many areas of science and engineering, as we will see shortly. Now, if you haven't come across line process before, right, at this point in the talk, just think of line process as a random collection of lines, right? We'll define it more carefully in a few minutes. Mathematically, what do we mean by it? Because if we are thinking of this as a stochastic object, we first need to endure distribution on it, which we'll do shortly. But since I have introduced this model sort of out of the blue, I think it is only fair to also look at other potential models and see why we chose this. So let's do that very quickly. There are, as I said before, many other ways of modeling or developing a stochastic model for road systems. Here, I'm just giving 4 of those examples. First is a random planar graph, which has been used in the prior work. Here, think of every node of this graph as an intersection. And when you connect 2 of these nodes with an edge, think of that edge as the road segment, which is connecting 2 intersections. So these type of models are useful for topological investigations. Then from the stochastic geometry literature, we have famous tessellations, Poisson Voronoi and Poisson Delaunay tessellations, which could be used to capture, again, this irregularity in the road layouts. And the last one is Poisson line tessellation or Poisson line process. And each have their own, unique advantages over the others. Some of these models will capture some specific aspects of the road system in a better way compared to the others. But at the end of the day, they are somewhat realistic in the sense that they do capture this unique feature of the road, that it is a road system, that it is composed of line segments. Right. And at the end of the day, because of the analytical tractability, Poisson line tessellation or Poisson line process has emerged as a preferred choice for modeling road systems. And we will make a connection with the landmark paper written by Francois in 1997, where this model was first proposed for road systems in the context of communication systems. Before I do that, let's look at a quick look at the history of line processes, right? Because if this is the model we are going to study for the next 40 minutes, let's understand where it all started from. One can actually make a connection of line processes all the way back to 18th century to Buffon's needle problem, right, where we study the intersection of a line segment with a parallel set of lines. But the modern theory of line processes can be traced back to Samuel Goudsmith's paper in 1945. And there is an interesting history behind that paper. Goudsmith's work was actually inspired by a question that Neils Bohr posed to him in the context of cloud chamber experiments. So if you have not been exposed to cloud chamber experiments, so these experiments are used to study the trajectories of subatomic particles. So you have a cloud chamber with supersaturated gas, and the condensation trails of subatomic particles are used to study the trajectories and hence the properties of those subatomic particles. And in the 1940s, Neils Bohr asked this question, that what is the chance that several independent tracks of subatomic particles intersect at the same point or appear to emerge from the same point? At this point now, we can sort of make sense of that question and actually give that probability quite precisely. But in the 1940s, this understanding wasn't there. Now, the need to answer this question actually vanished before Goudsmith made any progress, but it nevertheless led to this first paper on line processes by the title Random Distribution of Lines in a Plane, which was published in 1945. Now, if you look at the history of line processes since then, I have just mentioned some names, some of the more influential papers which have been written since then. Roger Miles made many influential contributions in 1960s when he studied the properties of random polygons formed by this line process. A lot of it was built on off of Goudsmith's work. And Roger Miles' work was extended further, for example, by Centello and Yanez in 1972, where Miles's work was focused on Euclidean spaces, and Centello and Yanez extended it to non-Euclidean spaces. Then there was work by Richards, which again extended Miles's results. And in 1967, Bartlett studied spectral analysis of point and line processes. And I wanted to mention this because based on our investigation, Bartlett is actually the first person to use the term line process in the literature. Then there was work by Davidson on stationary line processes. And if you trace all the way to 1997, this is where our very own Francois wrote a landmark paper on the use of stochastic geometry for communication systems, in which he was the one who proposed to use line processes for modeling road systems. And after Francois's work, in around maybe 15 years back or so, Volker Schmidt and his collaborators also applied line processes to the analysis of wired networks. And over the past 5 years, I would say many of the esteemed colleagues have picked up this topic and sort of building off of this 1997 paper. And some of them have already presented and some will, I'm sure, present tomorrow. So a lot of it is building on this history here. Let's talk about this 1997 paper a little bit. So as I said already, Francois proposed this new stochastic geometry approach. And one of the components of this approach was the ability to model mobile nodes, right? And this naturally brings forth questions about the number of vehicles in a fixed cell, number of cell boundary crossings, which is the handover rate in a given setting. So John time of the typical vehicle in a cell, which is related to the session time, for example, in a network. And a lot of these questions have recently been revisited, as we'll see in slightly different settings. So we'll make those connections as we proceed in the talk. Before we go there, let's revisit the question that I posed in the very beginning, right? How do we think about distributions on lines, right? If it is going to be a stochastic object, we have to end over distribution. So which is where this Poisson line process is going to be formally defined. Let's do that. We are going to do it in 2 dimensions. We have line L1 in 2-dimensional Euclidean space. This line L1 can be parameterized in terms of 2 parameters, rho and theta, where rho is the perpendicular distance from the origin and theta is the angle that that perpendicular makes with the x-axis, right? Now we can map this line onto what we call a representation space, or what is also called the phase space, which is a infinite cylinder basically. So on the horizontal axis of this representation space, you have the phase, right, going from 0 to 2 pi. And on the vertical axis, you have the distance, rho, going from 0 to infinity. Right, and in this space, each line is basically a point. So you have L1 line from the original space mapping onto a point L1 in the representation space. If you have multiple lines, you are naturally going to get multiple points in the representation space. And we know how to end over distribution onto a set of points, right, which is a point process. So if we start with the Poisson point process in the representation or phase space, it gives us a Poisson line process in the original space. So this is how we end over distribution onto a collection of lines. Now, coming on to finally the main object of this presentation, which is the Poisson Line Cox process. So what we do here is we start with a line process. We know how to define that, right? Again, remember representation space, you have a Poisson point process. If you map it to the original space, you get a collection of lines, right? So that is a line process. Now on each line, we place an independent 1D Poisson point process, right? These blue points that you see on this slide. Obviously, other point processes could also be used and have actually been used in the literature to model, for example, headway distance between the vehicles and so on. But we'll just start with the simplest possible process here, which is 1D homogeneous Poisson point process. Now, the locations of these points that you get, right, collection of blue points, they form a Poisson Line Cox process. Now, this can be used to model things like locations of vehicular nodes, locations of roadside units, locations of other infrastructure such as charging stations or gas stations deployed along the road. So as you can see, this connection that I'm making with the gas stations and charging stations, some of the cyber physical metrics, which we often don't care about in wireless communications, can also be studied using this model. For example, for how long will I have to drive until I reach the next charging station? So those type of questions can now be posed in the context of this model. And as I mentioned before, this model, Poisson Line Cox process, has been recently used by many of us. Here I'm just quoting two of the earlier papers, one by Vishnu and another by Changsik and Francois. Since Changsik has already presented, I'm assuming some of this already appeared in his talk. So it turns out that one of the desirable properties of this Poisson Line Cox process is its tractability. And I should actually say remarkable tractability. And just to highlight that, what I'm going to do is I'm just going to present the nearest neighbor distance distribution for this process. And then we will start connecting these results slowly to wireless networks. So as many of you already know, nearest neighbor distance distribution is just the distribution of the distance from the typical point to the closest point of the same process. Now, in this case, I should mention that we are using the Euclidean distance as the distance metric because we are going to change that to path distance towards the end of the talk, right? And because of the two facts that the points form a PPP on each line, and the lines themselves are a Poisson point process in the representation space, this calculation is actually not that hard. It's just a couple of steps. You condition on the line process and you calculate the nearest neighbor distribution and then you marginalize. So it's not terribly difficult to compute this distribution. But what it does is, once you have a handle on these type of distributions, you can very easily study some of the wireless metrics, things like signal to noise ratio, right? Let's ignore the interference for now. And let's say that this red point is connecting to its closest blue point, right? The vehicle is connecting to its closest RSU. If you know how far that RSU is, you can find the signal to noise ratio distribution easily, right? And that's directly a function of this nearest neighbor distance distribution. And as we'll see that this theme of tractability actually extends to other more complicated metrics as well, things like rate coverage, SINR coverage, and so on. And as I mentioned already before, in the first part of the talk, we will focus on the Euclidean distance. We are going to focus on power law path loss model, right? R to the power minus alpha, alpha being your path loss exponent. Okay, so let's start connecting this slowly now to vehicular communication network, where two types of links are going to be of specific interest to us. You have V2V links, right, where two vehicles are connecting to each other, and you have V2I links where vehicles are connecting to infrastructure links, right, or infrastructure nodes like RSUs or macro cells. Okay. So before we go to a full-blown V2X type of a study, I would like to walk you through a simpler example just to build intuition and also to convey one key message, which is the comparison of this PLCP with a 2D PPP, right? Basically, sort of indirectly answering the question, do we really need this complicated model, or can we live with a simple 2D model in vehicular networks? Okay. So in order to answer that question and also to build intuition, we are going to start with the bipolar setting on a line process. So here, think of these red diamonds as your transmitters, forming a Poisson Line Cox process. And each transmitter has its designated receiver in either of the two directions at a distance d, right? You could put a distribution on d, but we are going to assume that that distance is fixed. And what we are going to study is the performance of the typical link in this setting, assuming that your transmission probability is P, right? So in the right-hand side figure, the filled circles mean that those transmitters are transmitting, and the hollow circles mean that those transmitters are silent, right? So naturally, if more transmitters are silent, that means that your interference will be smaller, right? And for this setting, it turns out that you can do the success probability analysis without much effort. And this is just the success probability expression. I won't be going into all the details. It just basically captures the functional dependence over all the key system parameters. For example, this is the term that captures dependence on noise, sigma squared being the variance of noise. This is the term that captures interference from the nodes located on the same line as that of the typical receiver. Think of that as, say, the typical line, right, on which the typical receiver is located. Then you have the third term, which is interference from the nodes located on the other lines, right? But exact functional form and so on is not important. What was important here was that we were able to write this expression in a not so complicated form, right? But can we get some insights from this result? In order to do that, I'm going to use this success probability result to study area spectral efficiency. Let's define area spectral efficiency first. So in words, it is just the average number of bits that you successfully transmit within, say, per unit area. So mathematically, it can be written in terms of PC, which is my success probability, right? You have this log to 1 plus beta, which gives you the link rate, right? Spectral efficiency, bits per hertz. Then PC is the success probability, how many of those links are actually successful in communicating. And then you have this term lambda, which captures the number of nodes that are transmitting in a given area, right? Here, we haven't gone into all the terminology because of the time constraints, but mu L here is the density of the lines, which is basically the average line length per unit area, times P. P is the transmission probability, and lambda N is the density of the PPP on each of the lines. And if you plot area spectral efficiency as a function of P, something interesting happens. This nature of result is very well known, that if P is very small, right, and you increase P slightly, your area spectral efficiency should increase because your system is still not interference limited. So activating more and more transmitters in the network should help ASE. But then you're going to reach a point where interference starts dominating. And after that point, if you increase P further, then the benefits you're getting from activating more transmitters are less than the interference that they are generating. So your ASE decreases. But what I wanted to highlight here was something slightly different. So if you look at the optimal points, so this is the optimal point here for PLCP, the model that we are discussing today, right? This is the optimal P star at which we should be operating. And this is the optimal P star that you get from a 2D PPP. So we see that there is, roughly speaking, just eyeballing, maybe a 2x difference between these 2 points. So naturally, PPP directly is not a very good model unless you do some modifications to that, which we will discuss later. Just using a 2D PPP for vehicular networks is not a very good idea. Now, let's look at a slightly more general model, I think, which will be to which people working on CV2X can probably more closely relate to. So here we have 3 types of nodes. We have vehicles, we have roadside units, and we have cellular macro base stations, right? In terms of the spatial model, you can think of this as a 2-tier model where cellular macro base stations are modeled as a 2-dimensional PPP, Poisson point process, because your macro base stations are not really restricted to lie on the roads, right? They could, but they are not really restricted. Then you have vehicular nodes and RSUs, which can be thought of as the second tier. You can just superimpose those 2 processes and think of that as one Poisson line Cox process, which forms the tier 2. We are not going to go into lot of details of the analysis, but if you check the paper, the analysis considers a fairly elaborate setting involving log normal shadowing, transmit beamforming, selection bias, and in terms of the association, we consider maximum average biased power-based association. So as I said, I invite you to check this paper for more details if you are interested in this specific problem. But in the talk, I'll just focus on one of the metrics that we studied in this paper, and I'll try to provide some intuition and also expose some of the interesting stochastic geometry constructs which we haven't discussed in the talk yet. So I'm going to focus on the rate coverage, right? And as we all know, if we assume that channel capacity is achievable for any given link, then the rate for that link, which in this case is the typical link for the typical receiver, right, can be written as the form that I've given on the slide, log to 1 plus SIR. And then you multiply that with the resources that you're getting from the base station. So you can think of W here as the total resources or total bandwidth that you're getting from the base station. And it is divided by the load on that base station or on that infrastructure node. So J here is the load on that node, assuming that the resources are given fairly to all the nodes in that, all the receivers in that cell. Now, if you study rate coverage, it is basically just the distribution of this random variable R, right? It's the complementary CCDF, it's a complementary CDF, probability R bigger than some threshold. So what we are really trying to understand here is what fraction of nodes in the network can achieve a certain minimum rate, right? And this can be computed. So if you just condition on the load here, which is this term J, right? You can express it into two terms. You have the SIR coverage term, and then you have the load term, probability J equals to J, which is just the probability mass function of the number of users which are being served by a given infrastructure node, right? For the SIR coverage, I'm going to discuss something briefly, but we will go into some more details of the load here. And I should also mention here that once you condition on J, as many people working with stochastic geometry probably already realize, random variables SIR and J are actually correlated. So we are making sort of an implicit simplification here by assuming SIR and J to be independent, which is usually the case in the wireless literature. Okay. So in order to enable this analysis, what we did was in this paper in TWC, we studied the asymptotic behavior of the Cox process. So you have in the center, you have a Poisson Line Cox process. And what we showed was, if you look at the regime of high line density and low node density, using Choquet's theorem, you can actually establish a formal equivalence between PLCP and 2D PPP in the sense that your Poisson Line Cox process converges to a two-dimensional PPP in the high line density scenario, right? And in the low line density scenario, it converges to 1D PPP, which is much easier to see. Rather, I would say both are sort of, expected results. It's just that we established this in the paper. So what you can then do is, if you are looking at PLCP under palm distribution, you can model the other nodes on the other lines as a PPP using this equivalence result. And then you can model your own line as a 1D PPP, which is basically the enabler of the analysis that we did in this paper, using a union of 1D PPP and 2D PPP, 1D PPP modeling the typical line and 2D PPP modeling the other nodes. So we won't be going into the details of that or the proofs. You can check that. You can check the paper for more details. But what I would like to discuss is the load, right, which is the second component of this analysis. So we know that network resources are shared by multiple users in the network, right? And in order to convey the basic idea, we are going to consider a single tier network here, and then we will generalize this to the multi-tier setting in a minute. So here we have this orange square, which is the macro cell, right? and you have vehicles in this cell of this macro cell. And the vehicles are these blue circles. And these vehicles are described by a Poisson Line Cox process. Now, the load on a macro base station here is basically just the number of nodes lying in its Voronoi cell, which is the shaded part here. Right? And this calculation is actually quite interesting because it connects back to some of the well-known results in stochastic geometry, things like chord length distribution of the Poisson Voronoi tessellation studied by Stoyan in the 90s. So what you do here is you first study the total chord length distribution for the cell, right, which is the line segment, length of the line segments highlighted in dark brown here, and we will call it a random variable C. This is the total chord length, which is highlighted here. And then one can actually derive the probability mass function of the number of nodes located on these highlighted line segments in terms of the Laplace transform of the chord length distribution, which we recently did in this the paper that I'm highlighting here in 2020. So in this case, the load distribution is not at least that challenging, but it starts becoming more and more challenging as you go to a multi-tier setting, right? So in this picture, we have a two-tier setting, the one that we started with, right? Again, you have a macro cell, which is this orange square here, and then you have a line process on which the RSUs and vehicles are located. Now, what we are going to assume is that each RSU serves vehicles on their own road, right? Which means if you look at the service regions of those RSUs, those are line segments on the roads on which they are located. And if you now try to find the load distribution, it's a little more complicated because it's not just about counting the number of points located in this Voronoi cell. You also have to account for the fact that some of those points are being served by the RSU. So what we did is we actually found the distribution of the coverage cells, which are formed by these RSUs, and using that, we found the load on the macro cell, rather actually use the average load approximation in this case. And combining all the results, we then studied the rate coverage. And I'm just, in the interest of time, I'm just giving one representative result here. On the y-axis, we have rate coverage. And on the x-axis, we have selection bias for one of the tiers. And we noticed that the optimal selection bias, which is highlighted by this asterisk here, it could vary from 5 dB to 15 dB, depending upon your system parameters, your density of the lines, your density of the macro cells, and so on. So we have a lot more discussion in the paper if you are interested in going over it. Now, one of the questions that naturally comes up at this point is, do we know that this model is realistic, right? So sure, you have convinced us that this is tractable, but is it realistic, right? And if you don't have access to actual measurements, the next best thing you could do is to compare with what industry is doing, right? And we compared this model with the model that is used for 3GPP standardization. And for one representative scenario, this is the coverage probability that we got. This is the SINR distribution. And we noticed that the PLCP model and 3GPP model are, they are almost indistinguishable, right? If you match the parameters properly. And we have some more discussion on bridging this gap between the models that are used in the industry and in academia, meaning PLCP, in upcoming IEEE network paper, which will appear on IEEE Explore within a few days. Okay, so my last topic now, in the last few minutes, is departing a little bit from the Euclidean distance metrics and actually looking at path distance. What do we mean by that? Right, we have considered Euclidean distance until now, but it turns out, it has been shown in several papers, several propagation papers, that because of high propagation losses, millimeter wave signals through buildings, right, the dominant signal that you get at the receiver could be the one that travels along the street segments, it may not be the one that is dominant in terms of the Euclidean distance. It could be the one that travels along the streets, right? So it could be getting reflected or diffracted from the corners and reaching your receiver. So that could be the strongest one. Right? It has been shown, for example, in some of the measurements done by Andy Molish. It has also been used for some of the analysis by Robert Heath. So this inspired us to study the nearest neighbor distance distributions in the path distance sense, right, for this model, which we have done recently. So the problem we studied was consider a Manhattan Poisson line process, right, where your lines are horizontal and vertical for forming a PPP, right, on the x-axis and on the y-axis. And we studied the shortest distance in terms of the path distance from two reference points. One was arbitrary point of the MLCP itself, and another was the reference point, which was the typical intersection. Right? So we have exact results which appeared in the Journal of Statistical Physics in 2020. And using these results, we are now trying to describe some of the measurement results discussed in the previous slide, because this has interesting connections with geometry-based stochastic models. Right? Once you have some understanding of these distributions, you could come up with some analytical models for propagation in these settings. Right, so this is one of my last slides here, just comparing the Euclidean distance and path distance. It is quite different naturally, and I just also wanted to highlight the extremely simple forms that we get for this setting. And this is also corollary, meaning this is for the case where the reference point was the typical intersection. The more general result is obviously more complicated. And one can start asking many interesting questions once you have this some hold on these distance distributions. For example, what if you take the ratio of these Euclidean distance and path distance and you drive the node density to 0, right? How does this scaling behave? So I've been thinking about some of these questions as well. So if there is interest from anyone attending the talk, please write to me. I would love to discuss these type of questions. Okay, so with that, I think we are very close to the time also. So let me summarize this talk. In this presentation, we introduced line processes and Poisson Line Cox process. We used PLCP to model vehicular communication networks, and I gave some examples of the work that we have done on coverage and rate analysis. We also sort of demonstrated the relevance of this modeling and analytical approach to industry, right, by comparing with the models that they use. Also, some of the basic characterizations, such as the path distances, are fundamental in nature and may find applications in some other domains as well, such as autonomous systems and transportation, even sort of coming up with or planning for districts and so on, where to place your key infrastructure nodes. So those type of things can be studied using these models. So I have a couple of ongoing lines of work. I haven't really done much over the last year in this direction, but I do have these problems in mind if there is any interest from anyone attending the talk. Obviously, this one line of work, which I think is quite interesting, is the connections of PLCP with geometry-based channel models. Can we come up with some analytical models for propagation channels using these path distances that we are studying? And the second is this application of this general framework that stochastic geometry community has developed to cooperative perception. So really going into the sort of the cyber physical questions and trying to use some of these results within those bigger problems of cooperative perception. So last but not the least, I am very grateful to the National Science Foundation for supporting this research through this IISS grant. So these are the references if you are interested in checking some of our work. As I mentioned already, this short monograph we wrote is probably it sort of subsumes, I would say, most of the other papers I've listed here. So that would be a good first reference to start looking at this. All right, so with that, I would like to thank you all for your attention, and thanks again to Francois for this very kind invitation. And I would be happy to answer any questions. Thank you.
Thank you. Thank you very much. Are there any questions from the audience here? Yeah, we have a question from Francois. Sorry, just a second.
It's a joint question for Martin and for you first. So Martin gave a quite interesting lecture this morning on what he calls transdimensional analysis, I mean, stochastic geometry analysis, where he does something which seems connected to what you do, namely there is a, his point was that, I'm trying to rephrase what he said, that I mean, that you could consider what happens not on the road, on the, where you look at the typical point, as a two-dimensional point process, Poisson, with the ideas that far away could be looked at 2D and it simplifies things. But your scheme seemed to say that for the D2D case, there is a difference, right? Because I mean, if I get it correctly, I mean, you said that if you would.
Yeah, Francois, that's a very nice question. Okay, I got it.
Understand the connections between the two. So it's a twofold question to Mark. Right.
So first of all, let's see. Let's go back to this plot. Yes. So that's a very nice observation, Francois. So the difference here is, let me answer your second question first. When I compare it with the 2D PPP, it is just a 2D PPP which is matched to in density to your Cox process.
Yeah.
It doesn't have that one additional 1D PPP that captures your own line.
Okay.
So if you add that 1D PPP, I suspect that it will be very close to the Cox process, and I think it is a bit of a maybe chronological sort of an issue, because we did this work, did the D2D type of a setting before we did the other one, and Martin and I have had a couple of email exchanges since morning, and yes, we are actually looking at the same thing. And it just looks like that, at least that's my understanding from a very brief conversation over email that Martin and I had. So what he's calling a transdimensional model is exactly this union of 1D and 2D PPP that we used in this paper.
Okay, and so perhaps the curve is closer to the upper one, right? So yeah, that's what you mean, right? If you would look at this transdimensional analysis, you would have, if you.
It will be here. It should be somewhere here.
Right. Okay. Yeah.
Yep.
Okay. Thank you. Yes. Okay. I had another comment actually. For shortest path, there is a big literature in the algorithmic geometry community. People have studied lots of shortest paths on the Poisson Delaunay, on the Poisson Voronoi graph, and possibly on Poisson line processes. There was a survey lecture by somebody in Dunkirk a few months ago. I could send you references, but people in algorithmic geometry have entered into this geodesics on Poisson random graphs. And there is a dozen of papers. I will send you a few references and a few entry points. But this besides what you alluded to in terms of people coming from physics, there is this other community interested in that. Right. So that might be of interest to you. I didn't know this work of you with Detman, so it's new to me. So
okay. No, thank you so much, Francois. Yeah, I think that's very good feedback. I don't think I have looked at this algorithmic geometry papers in as much detail. I have come across some of the path distances, but I'll check the references that you will kindly share in more detail.
Yeah, so there is a linear growth, for instance, for the shortest path between 2 points. You stretch the 2 points, and you have a sort of discrepancy between Euclidean distance, and but it's a linear factor which is known For instance, on the Poisson Delaunay. It's so you might be interested in this literature. So we'll send references. Thanks.
Thank you so much, Francois.
Thank you very much.
Thank you, Anna.